A monster exists at the heart of nearly every galaxy. This is a journey to the edge of understanding, where physics gets wonderfully strange. By the end, you will grasp 25 astonishing truths about the universe's true titans, the supermassive and ultramassive black holes. We will uncover how a black hole can shine brighter than a trillion suns, and what happens when time itself begins to tear apart. What single idea about the cosmos fills you with the most wonder? Their sheer size is the first and most fundamental shock to our senses. We are not talking about something the mass of a star or even 1,000 stars. The largest black holes known to science, like Ton 618 and the Phoenix A cluster black hole, are so colossal they defy every earthly comparison. Their event horizons, the point of no return, are not tiny dots. They are spheres, vast cosmic domains. The event horizon of Ton 618 has a diameter larger than our entire solar system. To put that into a human scale, picture our sun as a small marble. On that scale, the orbit of Pluto would be a wide circle around it. The event horizon of Ton 618 would be a dark sphere even wider than that entire circle. You could fit every planet, every asteroid, every bit of space from the Sun to the distant Kuiper belt inside it with room to spare. This is not merely a dense object. It is a structure, a region of space so warped that within its borders, the very concept of outward direction ceases to exist. Light, time, and causality all turn inward toward a single, unknowable point at its center. We are beginning our list not with a simple fact, but with a redefinition of scale itself. This leads us directly to a second, crucial fact that corrects a widespread misunderstanding. The largest black holes in the universe are not simply the corpses of giant stars. They are an entirely different breed of cosmic entity. The black holes we often hear about, formed when a massive star explodes and its core collapses, are the stellar mass variety. They are heavy, yes, perhaps 10 or even 100 times the mass of our Sun. But to become a supermassive black hole, billions of times heavier than the Sun, you need a different recipe entirely. A single dying star, no matter how colossal, simply cannot provide that much material. So how did these titans come to be? The leading theories point to the chaotic nursery of the early universe. One compelling idea is direct collapse. In that primordial era, vast clouds of pure hydrogen and helium, undisturbed by the heavier elements that fill today's cosmos, could have collapsed under their own immense gravity. Instead of fragmenting into millions of stars, these clouds may have fallen inward all at once, directly forming a black hole seed thousands of times more massive than a star from the very beginning. It was a shortcut to bigness. Another path involves relentless growth through mergers and feasting. In the dense cores of the first proto-galaxies, many stellar black holes and massive stars could have been drawn together, colliding and merging over and over in a violent chain reaction. This seed, already hefty, would then have spent the next 13 billion years gorging on gas, dust, and entire stars, ballooning into the monsters we detect today. Their origin story is not a single dramatic death, but a saga of cosmic ambition that began when the universe itself was in its infancy. This deep connection between a black hole and its home galaxy brings us to a third fundamental truth. The largest black holes are not cosmic nomads wandering the void. They are permanent residents, the gravitational anchors at the very heart of their galaxies. Our own Milky Way, a majestic spiral of hundreds of billions of stars, is no exception. At its silent center, some 26,000 light-years away, sits our own supermassive black hole, Sagittarius A. It is relatively quiet and modest in size, but its presence is undeniable, its gravity dictating the orbits of the stars that swarm perilously close to it. This pattern holds true across the observable universe. From the smallest dwarf galaxies to the grandest spirals, Nearly every large collection of stars has a supermassive black hole as its central engine. But the true titans, the ultramassive black holes, seek out the most colossal galactic environments. They reign from the cores of giant elliptical galaxies, vast spheres of ancient stars that can contain 10 times the mass of our Milky Way. Even more incredibly, the very largest black holes we have discovered, like the one in the Phoenix cluster, make their home in the central galaxy of a massive galaxy cluster. Picture this: a galaxy cluster is not just one galaxy. It is a metropolis of hundreds, even thousands of galaxies, all bound together by gravity and swimming in an ocean of superheated gas. At the very center of this entire cosmic city, in the brightest, most dominant galaxy, sits the ultimate landlord. Its gravity not only controls its host galaxy, but also influences the flow of that searing intergalactic gas, heating it and preventing it from cooling to form new stars across the entire cluster. This black hole is not merely an occupant, it is the architect shaping the destiny of billions of stars and the future of an entire galactic neighborhood from its throne at the core. To truly grasp their power, we must understand the currency of cosmic weight, the solar mass. This is not a complex unit, it is beautifully simple. One solar mass is the mass of our own sun. It is the anchor of our solar system, the gravitational engine that holds all the planets in their graceful orbits. Its mass is so immense, it accounts for 99.8% of all the matter in our entire planetary neighborhood. Now take that staggering reality and multiply it, not by 1,000, not by 1,000,000, but by tens of billions. The largest black holes have masses measured in tens of billions of solar masses. The current heavyweight champion we know of is the black hole at the heart of the Phoenix cluster galaxy. Its estimated mass is 100 billion solar masses. Let that number settle, 100 billion. It is a 1 followed by 11 zeros. This means the Phoenix, a black hole, contains the equivalent mass of 100 billion stars, exactly like our Sun, all crushed and compressed into a single, unfathomable point of infinite density. To visualize this, picture every single grain of sand on every beach and in every desert on Earth. That number, in the trillions, still falls short of 100 billion. This black hole represents a concentration of matter so extreme, it warps the very fabric of space and time around it into a bottomless pit. Its gravity is the ultimate sovereign, dictating the motion of stars thousands of light years away and holding sway over an entire cluster of galaxies. Yet despite their reputation for darkness, these titans can become the brightest objects in the cosmos. This is our fifth astonishing fact. A supermassive black hole can shine with a brilliance that dwarfs its entire host galaxy. This paradox of light emerging from the ultimate dark is powered by one of the universe's most violent and efficient engines, an active galactic nucleus. The key is activity, a state of cosmic feasting. When vast rivers of gas, dust, or even entire stars are pulled by the black hole's immense gravity, they do not fall straight in. Instead, they swirl into a frenzied, flattened whirlpool called an accretion disk. Picture a celestial hurricane, but one where the friction and collisions are so intense that the material heats to millions of degrees. At such temperatures, matter does not just glow. It screams across the entire electromagnetic spectrum, from searing X-rays to brilliant visible light. This is the powerhouse of an active galactic nucleus. The most extreme and luminous form of this phenomenon is a quasar. A quasar is essentially a supermassive black hole in a state of gluttonous overdrive, an accretion disk so vast and energetic it can outshine the combined light of every single star in its galaxy. From a distance, the host galaxy itself becomes a faint smudge, a mere backdrop to the dazzling, point-like beacon at its core. These quasars are so phenomenally bright we can see them from the farthest reaches of the observable universe, their light having traveled for billions of years to reach our telescopes. When we observe a quasar, we are looking back to a more violent, energetic epoch of cosmic history, witnessing the raw, unbridled power of a black hole's feast. It is a stark reminder that in the cosmos, true darkness is not an absence of matter, but an absence of activity. But the most spectacular display of power from a feeding black hole does not come from the brilliant disk itself. It erupts from the poles, launching twin beams of matter into the void at speeds so close to light speed they appear to defy physics. These are relativistic jets, and they are one of the most violent and beautiful phenomena in the universe. Not every active black hole produces them, but when the conditions are right, the forces at play are unimaginable. As material spirals inward in the furious accretion disk, it generates magnetic fields of staggering strength. These fields become twisted and wound into colossal, focused tubes that erupt from the regions above and below the black hole's poles. Like a cosmic railgun, this magnetic funnel seizes a portion of the superheated plasma from the disk and blasts it outward in two opposing, needle-thin beams. The particles in these jets are accelerated to over 99% the speed of light. From our distant vantage point, we see these jets as brilliant, continuous streams stretching far beyond their host galaxy. The iconic image of the supermassive black hole in galaxy M87, the first ever captured, shows not just the shadow of the event horizon but also the base of its powerful jet, a testament to this ongoing eruption. In some galaxies, these jets can extend for hundreds of thousands of light years, punching through intergalactic space like celestial searchlights. Their impact is profound. When these beams slam into the thin gas that floats between galaxies in a cluster, they transfer enormous energy, heating the gas and preventing it from cooling and collapsing to form new stars. In this way, a black hole's jets act as a cosmic thermostat, regulating the growth of its entire galactic neighborhood. Furthermore, these jets are nature's most powerful particle accelerators, far beyond anything we can build on Earth. They hurl protons and electrons across the universe, some of which eventually reach our atmosphere as ultra-high-energy cosmic rays, messengers from the heart of a distant, ferocious engine. This profound warping of space and time around a supermassive black hole is not just a theoretical idea. We can see its effects with our own telescopes in a phenomenon that acts as nature's ultimate magnifying glass. To understand how, picture gravity not as a mysterious force pulling objects together, but as a curvature in the very fabric of the universe. A common analogy uses a stretched rubber sheet. Place a heavy ball, like a bowling ball, in the center of the sheet. It creates a deep dip. Now roll a marble near the edge of that dip. The marble will spiral inward, not because a force is pulling it, but because it is following the curved path created by the heavier object. In this model, the bowling ball represents a star, and the marble represents a planet or a beam of light. A supermassive black hole, however, is not a bowling ball. It is an infinitely dense point that creates a pit so deep and steep the sides become vertical, a bottomless well in the cosmic sheet. This extreme curvature does something extraordinary to light. According to Einstein's theory of general relativity, light, while traveling in a straight line, must also follow the curves of this warped spacetime. So when light from a distant star or galaxy passes close to a supermassive black hole, its path is bent. The black hole's gravity acts as a lens, distorting and magnifying the light from objects behind it. Astronomers call this gravitational lensing. The results are breathtaking. Sometimes we see a single distant galaxy stretched into a long, thin arc of light like a celestial smile. In rarer, perfect alignments, the light from the background object is bent into a complete circle around the black hole, a shimmering halo known as an Einstein ring. Other times, the same distant quasar might appear as 2, 3, or even 4 identical images clustered around the central mass, each one a ghostly duplicate following a different bent path through the warped space. This is not an optical illusion. It is a direct, observable validation of Einstein's century-old predictions, a cosmic signature written in bent light that proves spacetime itself is malleable. The largest black holes, with their unimaginable gravity, are the universe's most powerful lenses, twisting the light from the ancient cosmos into rings and mirages for us to decipher. Gravity's grip on light is only half the story. The true strangeness of a supermassive black hole extends its influence over time itself. As an object falls toward that ultimate point of no return, a profound and unsettling transformation occurs. For us, watching from a safe distance, the falling object would appear to slow down. Its descent would become a gradual, agonizing crawl. The light coming from it would stretch, shifting to longer, redder wavelengths until it finally fades from view entirely. This is not a trick of perspective or a failing of our instruments. It is a direct consequence of Einstein's relativity, a phenomenon called gravitational time dilation. Time, which we perceive as a constant, universal river, is actually a flexible stream, flowing at different rates depending on the strength of the gravitational field. Near a black hole where gravity is unimaginably strong, time flows far more slowly relative to the rest of the universe. Picture a hypothetical, indestructible clock falling toward the event horizon. For the astronaut brave or foolish enough to ride with that clock, time would feel normal. Their heartbeat would tick at its usual pace, their thoughts would flow one after the other. But for us, observing from afar with powerful telescopes, that same clock would tick slower and slower. The astronauts' movements would become like a video played at 1% speed. They would seem to freeze, suspended forever at the threshold of the black hole, their image stretched into an infinite, fading red smear. From our perspective, they never actually cross the event horizon. They become a permanent fossil in time, a testament to gravity's power to stretch a single moment into eternity. The astronauts' experience, however, would be terrifyingly different. For them, time passes normally. They would cross the event horizon in a finite amount of their own personal time, with no dramatic sensation, no flashing warning sign. The universe outside would, from their viewpoint, speed up in a blinding rush. Billions of years of cosmic history might flash before them as they fall inward, witnessing the future evolution of stars and galaxies in a matter of seconds. This is the ultimate paradox of the black hole. Two realities, both true, separated by the warping of spacetime. One observer sees a frozen statue. The other experiences a headlong plunge into the unknown. It forces us to abandon the comforting idea of a single, universal now. Near these titans, now becomes a personal experience, dictated entirely by where you stand in the grip of gravity. This distortion of time leads us directly to the most famous boundary in the cosmos, a line drawn by the laws of physics themselves. Every supermassive black hole is encircled by an event horizon. This is not a physical surface, not a wall of rock or fire. It is a mathematical threshold, a spherical shell of pure geometry marking the ultimate point of no return. The definition is elegant in its simplicity. The event horizon is the boundary where the escape velocity equals the speed of light. Think of escape velocity as the speed you need to break free from a planet's or star's gravitational pull. For Earth, that speed is about 11 kilometers per second. For a much more massive object like the Sun, the escape velocity is higher, over 600 kilometers per second. But at the event horizon of a black hole, the required speed to escape is the cosmic speed limit itself, 299,792,458 meters per second. Since nothing in the universe can travel faster than light, the conclusion is absolute. Once any form of matter or energy crosses this invisible line, its fate is sealed. It cannot send back any signal, any particle, any whisper of information. It is irretrievably lost to the outside universe, destined for the singularity at the center. This creates a profound information paradox that still puzzles physicists today. Everything that falls in, every atom, every star, every bit of data about its structure, seems to vanish from our reality, leaving behind only the black hole's mass, spin, and charge. It is as if the universe has a one-way shredder built into its fabric. This leads to a critical clarification about their nature. A common misconception paints black holes as cosmic vacuum cleaners, actively sucking in everything from vast distances. This is not accurate. Their gravity is governed by the same rules as any other massive object. From far away, the gravitational pull of a supermassive black hole is no different than the pull of a star or a planet of the same mass. If our Sun were suddenly replaced by a black hole of exactly the same mass, Earth and all the other planets would continue orbiting in their exact same paths, plunged into permanent darkness but not pulled inward. The danger only becomes absolute when you venture too close, crossing that final threshold where the rules of the game change forever. The event horizon is the gate, and it only swings one way. Yet beyond the event horizon, in the absolute darkness where physics as we know it fails, lies the ultimate enigma. This is the singularity, the theoretical heart of every black hole. According to the equations of general relativity, all the matter that has ever fallen in is crushed and compressed into a single point of infinite density. The word infinite is not an exaggeration here. It is a mathematical term signaling a complete breakdown. At the singularity, the curvature of spacetime becomes infinite, gravity becomes infinite, and our reliable models of the universe simply stop producing sensible answers. It is a place where the concepts of here and now, of before and after, lose all meaning. This presents one of the greatest conflicts in modern science because our other pillar of physics, quantum mechanics, which governs the bizarre world of the very small, utterly disagrees with this idea of a point of infinite anything. Quantum theory suggests that at such tiny scales, the very fabric of space and time should become fuzzy and grainy, not infinitely sharp. So which is correct? The truth is, we do not know. The singularity is less a physical object and more a glaring signpost that reads, "Here be dragons." It marks the frontier where our two most successful theories of reality, general relativity and quantum mechanics, meet and wage a silent war, each refusing to work in the other's domain. To resolve this, physicists are searching for a theory of quantum gravity, a single framework that can describe the fierce gravity of a black hole's core and the probabilistic dance of subatomic particles. Some intriguing ideas have emerged from this search. One possibility is that there is no true singularity at all. Instead, the crushing pressure might be halted by quantum effects, leading to an exotic, ultra-dense object sometimes called a Planck star or a bounce. In this scenario, the matter is compressed to an almost unimaginable density, but not to an infinite point. It might then rebound like a universe in miniature, though forever trapped behind the event horizon from our perspective. Another idea suggests the interior of a black hole could be a gateway to an entirely different region of spacetime. While these concepts sound like science fiction, they are serious attempts to answer a fundamental question. The singularity is not just a black hole's secret, it is a locked door, and behind it may lie the keys to a deeper, more complete understanding of the universe itself. The silent battle between our two great theories of physics hints at a reality where even the most solid objects are not what they seem. This quantum fuzziness might play a role in the most violent cosmic events imaginable, events that do not just tear stars apart but shake the very fabric of the cosmos. Supermassive black holes can merge, and when they do, they send ripples through spacetime itself. These are gravitational waves, and their detection opened a new window on the universe. Picture the most colossal dance imaginable. When two galaxies collide in a slow-motion ballet lasting billions of years, their central supermassive black holes are drawn together. They begin to orbit one another, swirling closer and closer in a tightening spiral. As they pirouette, they whip the fabric of spacetime around them like stones spun in a pond, sending out powerful, rhythmic ripples. These are not waves of light or sound. They are literal distortions in the geometry of the universe, stretches and squeezes in the distance between objects. Albert Einstein predicted their existence over a century ago, but he thought they would be too faint to ever detect. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, proved him wrong by sensing the tremors from two stellar mass black holes merging over 1 billion light-years away. That signal was a tiny chirp, a whisper from the void. Now imagine that whisper turned into a cosmic roar, a merger between two ultramassive black holes, each weighing tens of billions of solar masses, would be the most energetic event since the Big Bang. The gravitational waves produced would be so powerful they would momentarily distort the shape of our entire galaxy, stretching every star and planet by a tiny, almost imperceptible amount. These waves would travel across the universe for billions of years, carrying the signature of that ancient, catastrophic embrace. While we have not yet detected such a titanic merger, observatories are listening. Pulsar timing arrays, which use the incredibly regular flashes of distant dead stars as cosmic metronomes, are searching for the low-frequency hum of supermassive black hole binaries slowly circling each other in the hearts of distant galaxies. To catch the final, crashing crescendo of their merger would be to witness the universe ringing like a bell, a testament to the dynamic, violent, and deeply interconnected nature of all things. The gravitational waves from a merger are a fleeting tremor, but a supermassive black hole exerts a continuous, shaping influence on its cosmic home. This relationship is not one of simple dominance. It is a complex, symbiotic dance where the black hole and its galaxy grow together, locked in a feedback loop that dictates their ultimate size and fate. For decades, astronomers saw galaxies as collections of stars governed by gravity alone. The black hole at the center was considered a curious byproduct, a silent relic. We now know it is the opposite. The black hole is an active regulator, a cosmic thermostat that controls the very engine of star formation. This feedback mechanism is one of the most important discoveries in modern astrophysics. Picture a young, gas-rich galaxy. Vast clouds of hydrogen are cooling, collapsing under their own gravity, and igniting into brilliant new stars. Some of this gas also spirals inward toward the central black hole, feeding it and triggering an active phase. The black hole responds with ferocious energy. Its accretion disk shines with intense radiation, and it often launches those powerful relativistic jets. This outburst acts like a galactic scale wind. The radiation pressure and the jets blast into the surrounding reservoirs of star-forming gas, heating it, stirring it up, and in many cases blowing it completely out of the galaxy. This process is called quenching. By removing or overheating the fuel for new stars, the black hole effectively shuts down the star-forming factory in its own galaxy. It is a self-limiting cycle. The black hole's feast provides the energy for its own outburst, which then clears away the very gas that was feeding it, forcing the black hole into a period of quiet dormancy. This elegant feedback explains a mysterious correlation astronomers have observed. The mass of a galaxy's central bulge, the dense, spherical swarm of older stars at its core, is directly proportional to the mass of its supermassive black hole. A larger bulge means a larger black hole, a tight relationship that spans galaxies of all types. This is not a coincidence. It is a signature of that long, intertwined history of growth and regulation. The black hole and the bulge grew together, the black hole's outbursts periodically halting star formation, ensuring that the final size of one is a mirror of the other. In the largest galaxy clusters, this feedback is even more dramatic. The jets from the central black hole pump energy into the superheated cluster gas, preventing it from cooling and raining down to form new stars, thus governing the growth of not just one galaxy, but an entire metropolis of them. The black hole, therefore, is not a passive occupant. It is the architect of its domain, using its most violent outbursts to sculpt the galaxy that surrounds it, leaving a permanent mark on the structure of the cosmos. This architectural role explains why so many of these giants appear dormant. Not every supermassive black hole is a brilliant beacon of destruction. In fact, they exist in two distinct states, a fundamental split in their cosmic personality. Some are ravenously hungry and some are profoundly quiet. This difference comes down to a simple, brutal question of supply. An active black hole, like the famous Quasar 3C273, sits at the center of a cosmic buffet. Vast rivers of gas, clouds of dust, and even unlucky stars are funneled into its gravitational grip, creating that brilliant, swirling accretion disk and often launching those spectacular jets. This is a black hole in a state of feasting, and its brilliance is the glow of its meal. Our own galactic center, Sagittarius A, represents the opposite extreme. It is a quiescent or dormant supermassive black hole. For the most part, it sits in darkness, a silent titan surrounded by stars that orbit it peacefully. Its last major meal was likely millions of years ago. Today, it only receives occasional tiny snacks, perhaps a small cloud of gas or a stray asteroid, that create faint flickers of X-ray light as they are torn apart. This quiet state is not permanent. It is simply a phase in an ongoing cycle dictated by the environment. If a large molecular cloud were to drift too close, or if a star were to be nudged onto a plunging orbit, our quiet neighbor could awaken. Its dormant phase exists because the region around it has been largely cleared of the dense fuel needed for a sustained feast, likely due to past outbursts from the black hole itself or the gravitational influence of the surrounding stars. This cycle of feast and famine is universal. A black hole's activity is a direct reflection of its galactic neighborhood's density. In a gas-rich galaxy undergoing a collision, the central black hole will likely erupt into brilliance. In an older, elliptical galaxy where the gas has been used up or expelled, the black hole slumbers. Their hunger is always there, an eternal potential. Whether they shine or sleep depends entirely on what or who is on the menu. Even in its quiet state, a supermassive black hole's gravity holds a latent, terrifying power. This dormant violence is unleashed in one of the most spectacular events an astronomer can witness, a tidal disruption event. It is a cosmic cataclysm with a strangely culinary name, spaghettification. The process begins with a simple misstep. A star, orbiting peacefully in the crowded core of its galaxy, has its path perturbed. Perhaps a close encounter with another star sends it veering off course, directly toward the gravitational well of the central black hole. As the star approaches, it crosses a critical boundary called the tidal radius. This is the point where the black hole's gravitational pull on the near side of the star becomes overwhelmingly stronger than the pull on its far side. The difference in force is the key. Think of it this way. The gravity you feel from Earth is strongest at your feet and slightly weaker at your head, but the difference is negligible. Near a black hole, that difference becomes catastrophic. It creates an immense tidal force, a stretching pull that overcomes the star's own gravity, the very force that holds it together as a sphere. The star is literally pulled apart. It is stretched horizontally and compressed vertically, transforming from a majestic sphere into a long, thin strand of superheated gas, a cosmic piece of spaghetti winding around the black hole. This is spaghettification in its rawest form, the brutal reshaping of an entire sun by a gradient of gravity. The star does not go quietly. As it is shredded, a significant portion of its stellar material is flung out into space in long, luminous arcs. But a fraction of that gas remains trapped, falling back toward the black hole. This debris does not fall in smoothly. It collides with itself, swirling into a temporary, chaotic accretion disk that glows with an intense flare of radiation, often outshining its entire host galaxy for weeks or months. This brilliant flash is the tidal disruption event signature, a beacon in the darkness. For astronomers, these flares are incredibly valuable. They act as cosmic searchlights, illuminating the presence of a supermassive black hole that might otherwise have remained hidden, dormant, and invisible in the core of a distant galaxy. By studying the light curve and the spectrum of this flare, scientists can deduce the black hole's mass, the type of star it destroyed, and the physics of matter in the most extreme gravitational environment imaginable. Each tidal disruption event is a fleeting, violent experiment, a chance to watch a black hole's appetite in real time and measure its grip on the fabric of reality. That brilliant, destructive flash of a tidal disruption event is a fleeting glimpse of a black hole's power. But for decades, all we had were these indirect signatures, flares, jets, bent light. The ultimate proof, a direct photograph of the darkness itself, seemed like science fiction. Then, in April 2019, science fiction became reality. The world collectively held its breath as scientists unveiled the first ever image of a black hole. This was not an artist's impression or a computer simulation. It was a real photograph, a painstakingly assembled portrait of the supermassive black hole at the heart of galaxy Messier 87, 55 million light-years away. The image, a fiery orange ring of light encircling a dark central shadow, instantly became a global sensation, a shared moment of human awe and triumph. It looked eerily familiar, almost exactly as predicted by Einstein's equations over a century prior. Creating this image was a monumental feat of human ingenuity, a project that essentially turned our entire planet into a single, giant telescope. The Event Horizon Telescope collaboration did not build one massive dish. Instead, they synchronized 8 existing radio observatories across the globe, from the high deserts of Chile and Arizona to the peaks of Hawaii and the frigid landscape of Antarctica. By pointing all these telescopes at M87 at the exact same time and combining their data with atomic clocks, they created a virtual telescope as wide as Earth itself. This gave them the resolving power necessary to see something as incredibly distant and compact as a black hole's event horizon. The process was like trying to read a date on a coin in New York City while standing in Paris. A single telescope could not do it, but by linking telescopes worldwide, they achieved the sharpest vision in human history. The iconic image they produced shows exactly what theorists expected. The bright ring is not the event horizon itself. It is the intensely hot, magnetized gas in the accretion disk whirling around the black hole at nearly light speed. The darkness at the ring's center is the black hole's shadow, a region where light is bent so severely by gravity that it cannot escape, casting a silhouette against the brilliant background of the disk. This shadow is larger than the actual event horizon, a dramatic demonstration of spacetime's extreme warping. That single image did more than just make headlines. It provided the first direct visual evidence that these cosmic titans exist exactly as described. It confirmed the predicted size and shape of the shadow, offering powerful support for Einstein's theory of general relativity in the most extreme environment we have ever observed. It was a picture that changed our view of the universe, transforming black holes from theoretical phantoms into tangible, almost familiar landmarks in the vast dark. That first photograph of a shadow was a triumph of observation, but it also sharpened a deep theoretical puzzle. If a black hole is defined by just 3 simple numbers, what happens to everything else? This brings us to a deceptively simple idea with profound implications known as the no-hair theorem. The name is wonderfully odd, but its meaning is stark. It proposes that a mature, stable black hole can be completely described by just 3 properties and nothing more. Its mass, how much it weighs, its electric charge, whether it carries a positive or negative imbalance, and its spin, how fast it is rotating. According to this theorem, every other detail about the matter that formed the black hole or later fell into it is permanently erased. All the complexity of a star, the intricate patterns of a galaxy, the memory of what made you, all of that information is lost, shaved away. The black hole is left bald, featureless, defined only by those three numbers. Imagine throwing a grand piano, a library of encyclopedias, and a living oak tree into a blazing furnace. Once the fire dies, you are left with a pile of ash and some heat. You cannot tell what created that ash. You have lost the information about the piano's shape, the words in the books, the structure of the tree. The no-hair theorem suggests a black hole does something similar, but with the very laws of physics as its furnace. This elegant idea, however, collides head-on with a fundamental principle of quantum mechanics, which states that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This conflict is the heart of the famous black hole information paradox, a battle between our best theory of the very large and our best theory of the very small. If the no-hair theorem is correct, then black holes are the ultimate information shredders, violating a cornerstone of physics. If it is wrong, then black holes must somehow preserve information, meaning they must have hair, subtle features or structures that encode their history. So, which is it? Do these titans have hair or not? The debate is fierce and ongoing. Some physicists, like the late Stephen Hawking, originally believed the information was lost, leading to his famous bet against fellow physicist John Preskill. Hawking later conceded that bet, suggesting information might escape via a subtle, quantum mechanical process now associated with Hawking radiation. Others are exploring radical ideas. Could the information be stored on the two-dimensional surface of the event horizon, like a cosmic hologram? Or is it preserved in the chaotic quantum fuzz around the singularity? The quest to solve this paradox is not just academic gymnastics. It strikes at the nature of reality itself, asking whether the universe keeps a permanent record of everything that happens, or if some doors, once closed, are sealed forever. The answer may not come from looking at the black hole's shadow, but from listening to its faint quantum whisper. That faint quantum whisper hints at a hidden dynamism, a furious rotation locked within the darkness. While a black hole's mass defines its size and its charge is often negligible, its spin holds a special kind of terror. These titans are not static pits. They can whirl, and some do so at velocities that strain comprehension, spinning at a significant fraction of the speed of light. This spin is not random. It is a cosmic inheritance, a direct result of the conservation of angular momentum. Think of a figure skater pulling their arms in to spin faster. The same principle applies on a galactic scale. All the stars, gas clouds, and smaller black holes that have ever spiraled into the monster carried with them their own orbital motion. As they fell inward, that collective swirl became concentrated, transferred to the black hole itself, causing it to rotate faster and faster. A black hole born from the merger of two already spinning giants would emerge spinning even more rapidly, a product of that catastrophic dance. The theoretical maximum spin is set by the laws of physics. At this limit, the event horizon would spin so fast that its circumference would approach the speed of light. While we do not know if any black hole reaches this absolute extreme, measurements of some supermassive black holes suggest they are spinning at over 90% of the maximum possible rate. This is not a gentle rotation, it is a vortex of spacetime itself. The consequences of this spin are profound, thanks to an effect predicted by Einstein's theory called frame dragging. A massive rotating object does not just sit in spacetime, it churns it like a spinning spoon in a thick fluid. The fabric of the universe gets dragged around with the rotation. For a supermassive black hole spinning near its limit, this effect is monstrous. Close to the event horizon, spacetime is not just curved downward into a well. It is whipped into a frenzied whirlpool, forced to rotate along with the black hole. This creates a region just outside the event horizon called the ergosphere, a zone where dragging is so powerful that nothing can stand still. Every particle, every bit of light is compelled to move in the direction of the spin. It is a cosmic maelstrom where stationary is an impossible concept. This ferocious rotation directly shapes the black hole's most dramatic displays. The accretion disk of infalling gas is forced to align with the black hole's equatorial plane, but within the ergosphere, the dragging of spacetime can tear the inner parts of the disk into even more complex, turbulent structures. More strikingly, the black hole's spin is the likely power source for its most energetic feature, the relativistic jets. The twisting magnetic fields generated by the whirlpool of the accretion disk can tap into the rotational energy of the black hole itself, using it like a colossal battery to launch those narrow beams of plasma from the poles at near light speed. A faster spin means a more powerful battery, potentially creating longer and more brilliant jets. So when we see a galaxy with spectacular jets stretching across millions of light years, we are likely looking at the signature of a supermassive black hole that is not just massive, but spinning at a terrifying, universe-warping clip. Its rotation is the engine behind the beam. This terrifying spin is a monument to permanence, a vortex that seems to last forever, but even these cosmic titans are not eternal. Their reign, measured in billions of years, will eventually meet a quiet quantum end. This revelation comes from one of the most profound ideas in theoretical physics, Hawking radiation. It proposes that black holes are not perfectly black. They can, in theory, glow with a faint heat and slowly evaporate. The mechanism is a bizarre but beautiful consequence of marrying Einstein's gravity with the strange rules of quantum mechanics. Empty space, according to quantum theory, is not truly empty. It is a seething, frothing sea of virtual particles. These are particle-antiparticle pairs that constantly wink into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and returning the energy. This quantum jitter happens everywhere all the time. Now bring a black hole's event horizon into this picture. Imagine one of these virtual pairs popping into existence right at that fateful boundary. In the fraction of a moment before they recombine, one particle falls across the event horizon, lost forever to the outside universe. Its partner, however, is left stranded outside. With nothing to annihilate with, this orphan particle becomes real. It gains the energy needed to exist permanently, and it radiates away from the black hole. To an outside observer, it looks as if the black hole has just emitted a particle. But the energy for that particle came from the black hole's own gravitational field. To conserve energy, the black hole must lose a tiny, tiny amount of mass. This is Hawking radiation, a slow, quantum leak from the most secure vault in the cosmos. The process is unimaginably slow for any black hole we know. For a stellar mass black hole, the temperature of this radiation is a fraction of a degree above absolute zero, and the time required for it to completely evaporate is many, many times longer than the current age of the universe. But for the largest supermassive and ultramassive black holes, the scale is almost beyond comprehension. Because a black hole's temperature is inversely related to its mass, the bigger the black hole, the colder it is and the slower it evaporates. A black hole with the mass of our Sun might take 10 to the 67 years to vanish. A monster like the one in the Phoenix cluster, weighing 100 billion solar masses, would take a time so vast it makes the lifetime of stars seem like the blink of an eye. We are talking about timescales where the universe itself will have grown cold and dark, where all stars have burned out and galaxies have drifted apart. In that distant, frozen epoch, these last surviving titans will finally begin to fade, their immense mass dissolving into a faint, final whisper of particles, marking the quiet end of an era that once shaped the cosmos. Hawking radiation suggests even black holes are not permanent, but their story may have begun far earlier than any star. This leads to a wild and speculative possibility, one that connects these titans to the universe's greatest mystery. Could some black holes actually be the hidden fabric of the cosmos itself? we are venturing into the realm of primordial black holes, a hypothetical idea with profound implications. These would not be the descendants of dead stars. Instead, they are thought to be fossils from the universe's violent birth, formed in the first fraction of a second after the Big Bang. In that unimaginably dense and hot primordial soup, tiny, random fluctuations in density could have been so extreme that regions of space simply collapsed directly under their own gravity, pinching off into black holes. These would have been born with a wide range of sizes, from microscopic specks to masses far larger than any star. This is where the speculation ties into dark matter. We know dark matter exists because of its gravitational pull on galaxies and galaxy clusters, but we have never directly detected what it is made of. For decades, the leading candidates have been exotic subatomic particles. But what if part of the answer is not a particle at all, but an ancient, scattered population of these primordial black holes? They would be dark, they would have mass, and they would exert gravity, perfectly matching the basic description of dark matter. They would be hiding in plain sight, or rather, in plain darkness, drifting through galactic halos and between galaxies. The idea is elegant, but reality has placed severe constraints on it. If vast numbers of planet-sized or asteroid-sized primordial black holes filled our galaxy, they would occasionally pass in front of distant stars. Their gravity would act as a lens, causing the star's light to briefly magnify and brighten in a phenomenon called microlensing. Astronomers have conducted extensive surveys looking for these telltale flashes. While a few candidate events have been seen, there are simply not enough to account for all the dark matter. The universe seems to have left a note saying, "Not this way, at least not for most of it." Still, the door is not completely closed. A population of primordial black holes in a very specific mass range, or perhaps a mix of sizes, could still contribute a portion of the unseen mass. It is a captivating thought that some of the dark matter holding galaxies together might not be an unknown particle, but the cold, dark remnants of the universe's first chaotic moments. Even the most ravenous appetite in the cosmos faces a natural limit. The universe has built-in regulators that prevent a supermassive black hole from growing indefinitely, no matter how much fuel surrounds it. One of the most fundamental is known as the Eddington limit. This is not a law about the black hole itself, but a balance of forces in the material trying to feed it. Picture a black hole pulling in a thick, steady stream of gas. As that gas spirals inward and heats up in the accretion disk, it shines with incredible brilliance. That light exerts a powerful outward pressure, radiation pressure, that pushes back against the infalling gas. The Eddington limit is the precise point where this outward push of light exactly balances the inward pull of gravity. It is the maximum sustainable feeding rate. If the black hole tries to eat faster than this, the intense radiation from its meal will actually blow the surrounding gas cloud away, cutting off its own food supply. It is a cosmic case of biting off more than you can chew. For the largest black holes, this limit is staggering but finite. A black hole of 100 billion solar masses could, in theory, consume several solar masses worth of gas every single year, shining with a luminosity that outshines entire galaxies. Yet even at this incredible rate, there are other, larger constraints. The most effective brake on a black hole's growth is its own success. The powerful feedback from its active phases, those brilliant quasars and relativistic jets, acts like a galactic-scale hurricane. It sweeps through the core of the galaxy and the surrounding cluster, heating and dispersing the very reservoirs of cold gas needed for future feasting. A black hole can essentially starve itself into dormancy by being too effective at its job. This creates a natural cycle of feast and famine that self-regulates its growth over billions of years. Furthermore, in the vast, ancient elliptical galaxies and clusters where the largest black holes reside, most of the usable fuel has already been consumed or expelled. The cosmic pantry is simply running empty. All of this points to a profound conclusion. The largest black holes we have discovered, like the 100 billion solar mass Titan in the Phoenix cluster, might not be rare freaks of nature. They could represent a natural ceiling, a cosmic size limit that black holes can reach given the age of the universe and the available material. They have grown as large as their environment and their own physics will allow. They are the ultimate products of a 13.8 billion-year-old universe, sitting at the pinnacle of what gravity and time can possibly build. Their ultimate size limit makes them cosmic landmarks, but that same immensity also makes them the universe's perfect lighthouses. The brilliant glow of a distant quasar, powered by a feeding supermassive black hole, does more than just announce its own existence. It pierces the darkness between galaxies, illuminating the hidden architecture of the cosmos itself. Astronomers use these quasars as backlights, a technique that transforms their light into a detailed map of everything it passes through. Here is how it works. When the intense beam of light from a quasar travels billions of light years to reach us, it does not travel through empty space. It passes through the diffuse clouds of gas that float in the vast voids between galaxies, known as the intergalactic medium. This gas is mostly hydrogen, the universe's most basic building block. As the quasar's light passes through these clouds, the hydrogen atoms absorb very specific wavelengths of that light. Each absorption leaves a unique fingerprint, a dark line in the quasar's otherwise smooth spectrum of colors. Because the universe is expanding, these gas clouds are all moving away from us at different speeds. This motion stretches the absorbed light, shifting each dark line toward the red end of the spectrum by a precise amount. The result is breathtaking. Instead of a single absorption line, the spectrum of a distant quasar shows a forest of hundreds, even thousands of these dark lines, each one redshifted by a different amount. This is the Lyman Alpha Forest, a dense thicket of lines that tells an epic story. Each line corresponds to a specific cloud of hydrogen at a specific distance along the line of sight. By decoding this forest, astronomers can reconstruct a one-dimensional core sample of the universe. They can determine where these clouds are, how much gas they contain, and how they are distributed across cosmic time. This map reveals the large-scale structure of the cosmos, the vast cosmic web of filaments and voids that forms the skeleton of the universe. The supermassive black hole, by virtue of its brilliant feast, provides the flashlight. The absorbing gas clouds are the objects in the room, and the spectrum is the photograph. Without these distant, monstrous engines shining their light across the eons, this hidden framework of creation would remain forever in shadow. That brilliant beam of light illuminating the cosmic web can, from the perfect angle, become a weapon aimed directly at us. When the universe aligns a specific type of active galaxy just right, it creates the most powerful, persistent explosions we have ever detected. These are blazars, and they represent a supermassive black hole in its most ferocious and focused state. Recall those relativistic jets, the beams of plasma launched at near-light speed from the black hole's poles. In most active galaxies, those jets shoot out into space at some oblique angle to our line of sight. But in a blazar, a remarkable and rare cosmic coincidence occurs. One of those jets is pointed almost directly at Earth. We are staring straight down the barrel of the universe's most powerful particle cannon. This precise alignment transforms our view completely. Effects that would be subtle from the side become overwhelmingly bright and dramatic due to a phenomenon called relativistic beaming. Because the jet's material is moving toward us at such a tremendous fraction of light speed, its radiation is concentrated, amplified, and squeezed into a much shorter time frame. It is like the difference between hearing a siren from a passing ambulance versus hearing it as the vehicle speeds directly toward you. The sound is louder and the pitch is higher. For a blazar, this means the jet appears thousands of times brighter than it would from any other angle. outshining not only its host galaxy, but often every other source in its region of the sky across the entire electromagnetic spectrum. This beaming also explains their most distinctive characteristic, extreme variability. The brightness of a blazar can change dramatically over days, hours, or even minutes. A single blazar can double its brightness in gamma rays in a matter of hours, then fade just as quickly. This flickering is the signature of turbulent storms within the jet itself, shocks and collisions between clouds of high-energy particles, their light boosted and compressed by their headlong rush toward our telescopes. Because we are looking directly into the jet, we are witnessing every flare and eruption in real time, a front-row seat to a continuous cosmic detonation. The energy involved is almost beyond comprehension. Blazars dominate the high-energy sky, emitting staggering amounts of gamma rays, the most energetic form of light. They are also prime suspects as the sources of ultra-high-energy cosmic rays, single subatomic particles carrying more kinetic energy than a professionally thrown baseball. These particles are accelerated in the jet's magnetic fields to energies millions of times greater than anything achievable in human particle colliders. For astrophysicists, blazars are more than just dazzling lights. They are extreme natural laboratories, testing grounds for physics under conditions we could never hope to recreate. By studying their flickering light and dissecting their spectra, we probe the mechanics of particle acceleration, the structure of magnetic fields in relativistic flows, and the very processes that funnel matter and energy from a black hole's accretion disk into those narrow, devastating beams. Every flicker from a blazar is a data point from the edge of physics, a message from a beam of focused fury that has traveled across the cosmos to tell us just how violent and energetic a quiet point of darkness can truly become. Our own galactic center holds a surprisingly gentle giant, Sagittarius A star, the supermassive black hole anchoring the Milky Way, weighs in at a modest 4 million solar masses. For decades, its existence was a compelling theory, inferred from the frantic motions of stars and gas in the galactic core. But the definitive proof, the evidence that clinched a Nobel Prize, came from watching individual stars dance around an invisible point. Astronomers, using ever more powerful telescopes, track the orbits of stars like S2, which makes a blistering loop around the galactic center every 16 years. By meticulously charting these stellar paths over decades, they could apply the same laws of gravity that govern our solar system. The stars were not orbiting a cluster of dim stars or a cloud of dark matter. Their elliptical trajectories, swinging at speeds over 5,000 kilometers per second at their closest approach, could only be explained by a single, incredibly compact object of 4 million solar masses. The mathematics left no room for doubt. A supermassive black hole was the only possible conductor for this stellar orchestra. This painstaking work provided the first direct kinematic proof of a black hole's existence at the heart of a normal galaxy, transforming Sagittarius A star from a hypothetical entity into a measured cosmic fact. Yet despite its proven power, our resident Titan is remarkably tranquil. Unlike the brilliant quasars or blazars in distant galaxies, Sagittarius A star is a faint radio source emitting only a trickle of energy. It is in a deep state of quiescence, a sleeping dragon. This quietude is a matter of circumstance, not nature. The region around it has been largely swept clean of the dense, cold gas needed to fuel a major outburst. The stars that orbit it are mostly on stable paths, not plunging in to be devoured. It receives only the occasional snack, a small cloud of gas, a wandering asteroid, which creates a faint flicker of X-rays as it is stretched and heated before vanishing. But geological and astronomical records suggest this was not always the case. Evidence points to a more active past. Observations from space telescopes have detected giant, glowing bubbles of gamma rays extending thousands of light years above and below the galactic plane, structures likely inflated by an energetic outburst from Sagittarius A star within the last few million years. There are also signs in the distribution of certain elements that suggest a significant flare occurred perhaps just a few centuries ago, a time when human astronomers were only just beginning to turn telescopes to the sky. Our black hole, it seems, has cycles. It can slumber for millennia, then awaken to a modest feast, reminding the galaxy of the latent power at its core. Its current gentle state is a gift, offering us a stable, close-up laboratory to study the immediate environment of a supermassive black hole without being blinded by its fury. This well-behaved neighbor allows us to test our theories of gravity and accretion in a unique, quiet detail, all while knowing that even the calmest giant can sometimes stir from its sleep. That quiet, well-behaved giant in our galactic center presents a serene facade, but it hides a conceptual storm that strikes at the heart of physics itself. The information paradox is not a minor puzzle. It is a fundamental crisis, a direct conflict between the two pillars of modern science. On one side stands general relativity, with its elegant geometry and its declaration that black holes are simple, defined only by mass, charge, and spin. Everything else about the matter that falls in the chemical composition of a star, the DNA of a hypothetical astronaut, the text of every book ever written is erased, shredded by the singularity. This is the no-hair theorem in action. On the other side stands quantum mechanics, the rulebook for the subatomic world. One of its most sacred principles is unitarity, the idea that information is never truly lost. It can be scrambled, hidden, or transformed into an incredibly complex form, but in principle it must always be recoverable. You could burn a book to ashes, but a hypothetical, all-knowing physicist could, in theory, analyze the smoke, the heat, and the ashes to reconstruct every single word. Quantum mechanics says the universe keeps perfect records. Black holes, as described by general relativity, appear to be the universe's one perfect shredder. So who is right? This is not an abstract debate. The fate of our understanding of reality hangs in the balance. If information can be lost forever in a black hole, then quantum mechanics is flawed, and we must rebuild physics from the ground up. If information must be preserved, then our picture of black holes is incomplete. Something must happen to encode that lost data. This paradox is the engine driving some of the most profound theoretical work today, pushing scientists toward a grand unified theory of quantum gravity. Candidates like string theory and loop quantum gravity are attempts to reconcile these warring giants. String theory suggests that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. In this framework, the information of what falls into a black hole might not reach the singularity at all. Instead, it could be smeared and stored on a vibrating fuzzball that replaces the classic event horizon, or encoded in the quantum states of these strings at the boundary. Loop quantum gravity, another approach, proposes that spacetime itself is not smooth and continuous, but woven from tiny, discrete loops. At the Planck scale near the center of a black hole, this granularity of space might prevent the formation of a true singularity, creating a bounce or a transition to another region of spacetime, preserving information in the process. The late Stephen Hawking himself wrestled with this paradox for decades. He initially believed information was lost, famously stating it meant the end of predictability in science. Later, he changed his mind, proposing that information might slowly leak out in the subtle, scrambled form of Hawking radiation itself. Think of it like burning an encyclopedia. The information seems gone, but it is actually encoded in the precise pattern of the light and heat given off, a pattern so complex it appears as random noise. Decoding Hawking radiation to read that cosmic encyclopedia, however, is a challenge far beyond our current reach. The black hole information paradox forces us to confront the limits of our knowledge. It tells us that our two most successful theories are, in their current forms, incompatible. Solving it is not about fixing a small error. It is about discovering a deeper layer of reality, a set of rules that work where gravity is strong and quantum effects are fierce. The answer, when it comes, will not just tell us what happens to a particle that crosses an event horizon. It will reveal how the universe itself keeps its books. The paradox of information loss is not a dead end but a signpost. It points toward a deeper truth, our 25th and final fact about these cosmic titans. Supermassive black holes are more than just monsters or engines. They are the universe's ultimate physics laboratories, windows into the fundamental laws that govern all of reality. Every extreme characteristic we have explored, from the warping of spacetime to the evaporation via Hawking radiation, is not just a spectacle. It is an experiment running on a cosmic scale that we are only now learning to observe. Think of it this way: on Earth, we build massive particle colliders and intricate detectors to probe the rules of nature. We smash particles together at incredible speeds to see what emerges, testing our theories in controlled, if extreme, conditions. A supermassive black hole is nature's version of this, but on a scale we could never hope to replicate. It creates conditions of density, gravity, and energy that are impossible anywhere else in the present-day universe. By observing how matter and light behave in its grip, we are effectively running tests on the theories of Einstein, Hawking, and countless other physicists. The bending of light into Einstein rings tests general relativity's predictions about gravity with a precision no Earth-based experiment can match. The flickering glow of an accretion disk probes the turbulent physics of magnetized plasma. The faint, theoretical whisper of Hawking radiation, if we could ever detect it, would be a direct observation of quantum effects married to intense gravity, a glimpse of the theory we desperately need. This makes black holes unique crossroads. They sit at the intersection of the universe's largest and smallest scales. Their immense mass shapes galaxies and clusters, the domain of cosmology. Yet their deepest secrets are locked in quantum processes at their cores, the domain of the infinitesimally small. To understand them fully, we must forge a single theory that can describe both realms simultaneously, a theory of quantum gravity. Every observation, from the shadow in the M87 image to the timing of a pulsar near a black hole, provides a crucial data point for this grand quest. They force our most brilliant minds to ask the most profound questions. What is the true nature of spacetime? Is it smooth, or is it granular at the smallest scales? Does time have a beginning, and what does it mean for it to end at a singularity? What is the ultimate fate of information in our universe? By pushing us to these frontiers, black holes do more than just consume light. They illuminate the path forward for all of physics. They are not merely destinations for wayward stars. They are guides, challenging us to look beyond our current understanding and daring us to discover a more complete picture of reality itself. In their profound darkness, we find the brightest questions. From that final, mind-bending frontier of physics, our journey through 25 astonishing truths about the universe's largest black holes reaches its destination. We began with sheer scale, confronting spheres of darkness wider than our solar system. We witnessed cosmic power, from quasars outshining galaxies to jets that sculpt entire clusters. We grappled with the warping of space and time, where light bends into rings and moments stretch into eternity. We met the silent regulator in our own galactic core, and the ferocious blazar aimed like a cannon at Earth. Each fact peeled back a layer, revealing these titans not as mere destroyers, but as architects, engines, and the universe's most demanding laboratories. They are central characters in the grand story of everything, shaping galaxies from their birth and challenging the very foundations of our knowledge at their mysterious hearts. So we turn the question to you. After this voyage from the event horizon to the edge of theoretical physics, which single fact reshaped your understanding of the cosmos the most? Was it the sheer size of Ton 618, the haunting idea of spaghettification, or the paradoxical whisper of Hawking radiation? Let us know in the comments below. If exploring the deepest mysteries of space lights up your curiosity, be sure to subscribe for more journeys to the edge of understanding. As you look up at the night sky, remember that scattered across that immense darkness are these profound wells of gravity and mystery, silent engines around which the story of the universe quietly turns.